Morning, everyone in Australia, and good evening, American friends. I'm just trying to find a picture to show you, but because I'm away from home, I'm in Canberra, and I'm on an iPad, and my files are not available as usual, so we'll just have to make do. I've got one apology, and I'll find who that was from in a moment. So while I get organized, I'm just looking around who we've got in Australia, and I can see Duncan is there. And I think that's all, just the two of us. Very, very light. And some people might join us. Duncan, do you want to kick off, or just while I get organized at this end? And we hope your microphone's working today. Not. No, it's not.
I think I'll have to change computers someday.
No,
is that right working?
Now. Yep, that's working.
Yeah, it's a bit unknown cause. Yep. What have I been doing for the last month? In the radio world, I guess I've been battling radio frequency interference. And I've had to I'm in the process of abandoning the band I was using at 900 megahertz to return to another band. So I've been doing an RFI survey. So the data for the Vela experiment has been, it's not unusable, but a lot of data has just been thrown away because the data points are being scattered. So I'll probably move down in the next couple of days and do some tests to see what the RFI level is at the radio astronomy sensitivity. I already know at normal operating levels, which would be for communications, it's okay, but you have to peel the onion, and there's going to be some tears I can see in the future on this one. So I'll probably move down into the 830 megahertz band, which seems to have been vacated by the users at the moment, at least to a reasonable level. The nature of the interference was sometimes narrow band impulsive, sometimes broadband and sitting there, and would fade out. I interpret that probably I was receiving a signal from a mobile handset of some kind. It had that had a user behavior. The character and some of the characteristics of the interference was what they call a ratch, like a number of pulses, and it that would go on for a little while, like something was trying to hook up and then died out. Other times it was pretty severe in the total power of the autocorrelation of the system. So I've been looking at that, and also been working with some people on taking SDRs into record solar activity in the 15 to 88 megahertz region. The system's capable of going further, but it's really a cadence problem. How fast do you want to do it to record that? So that's reasonably reliable with the SDR. So basically I'm doing a Fourier transform of 8 megahertz, then jumping 7 megahertz, the next center frequency. So I don't get the roll off on my band, on the passband, the digital passband edges into the data. And I'm working with Jimmy Fitzpatrick in Scotland on that, and there's some interest from Manuel, who's works in Spain, on that one. So we just, and this is not at the not at the GNU radio level. We're actually going down to the API level in the software, which I find painful because I only write C and not C++, and I'm not a great programmer. But yeah, we're getting there. So the final stage of that is that I can see the sky. And the other function of this was trying to calibrate the antenna by putting a switchable noise source across the antenna terminals and raising the noise floor to a known level. So you can sort of start getting a calibration of one of these. I think it's an LWA derivative antenna for getting a scale for the instrument. So that's what I've been up to.
Yeah, thanks, Duncan. Sounds like you've got plenty on there. The RFI is a real problem, as we know, and getting worse. I think the best news of the week was that the Starlink system went down for a while. And that probably reduced RFI for a while. So, any questions around for Duncan while he's with us and his microphone's working? No, nothing. Rob,
hang on,
yeah,
could
sorry,
I ask a question? Sorry, it's Mark here in sunny Stockport, England.
Yeah, go ahead, Mark. Yep.
Oh, sorry, switch my video on, you can see me. Hi there. I'm struggling with this RFI. I've only started radio astronomy back in June. I'm still not familiar with all this SDR stuff. I've been speaking in depth with Alex Pettit. He's been advising me, and he advised me to get a 50 ohm termination, put it on my Sawbird and SDR tuner, and run SDR sharp, look at the levels on SDR sharp, and then take the 50 ohm termination off. I was supposed to see 3 dB difference between with the termination on and the termination off. I can see that, but I can't tell if there's a lot of noise. All I know is when I try and do this drift scan, I'm not getting very much data. It seems to be swamped with noise. Tomorrow I'm going to try in this RFI noise, low noise area. We've got a sort of garden near us where there's not many buildings, and I think that should be fairly low in RFI. I should try just a short scan tomorrow.
Okay.
How do you actually quantify this noise?
How do I quantify it?
Or how do I measure it? I mean,
yeah, you can measure it in just the peak deviation of what's going on. And if it's anthropomorphic, if it's person induced, it will have a signature on it. I had a lot of experience with looking at handset interference on a very sensitive radio telescope as a professional. And the things you look for are not measuring so much, but simple things like time of day, whether it goes up around commuter time, lunchtime, dinner time, whether it fades away 11 o'clock onwards, where it's quite quiet in the morning. And that's an encoded signature on it that tells you something about the likely origin of it. Not saying it is. And and then I'll go on to say there are 2 types of RFI. There's your self RFI, when you do yourself in by the devices we use to record the signal, and there's the external stuff. The other comment I make is while you're doing this, just be a little bit careful about how much bandwidth you accept until you get a feeling for the RFI environment, because RFI will just, as you alluded to, pump up your system temperature. And it does it linearly, just raises system temperature. So,
Can I share you quickly some images?
it's all right, Paul?
Yeah, far away. Yep, all good.
Screen 2.
So while the images are coming up, so
Can you see
handsets
that?
have not at the moment.
Yeah, there they are.
Okay.
So this is SDR sharp. All I've got
Yep.
connected is this Noelec SDR and this Sawbird. So I've got no termination and with termination. The bottom 2 images are with termination and the top 2 without. But
Okay.
what on
Go
earth
on.
can I see here? I can see
Oh,
these
well,
are missing, these peaks in
yeah.
the
Okay.
quiet location. Yeah.
So what I see, I can't see the scale, but I think you need to open the scale up. You don't need the top half of the scale. You've got it centered halfway down, but you need to expand that scale to start looking at it. Now,
You mean this scale?
yeah, the scale, vertical scale, you need to widen it out to have a bit of a look at it. And there are things like we have SDRs. SDRs have their own fingerprint, noise
Yeah.
fingerprint. If you're too close to that, if your signal's not dominating that noise coming out of the receiver, then you'll see it in your passband. So you'll see on the characterization I'd use is there are intermittent interferers. There are carriers that are there all the time, and those carriers sometimes can be related back to your instrument. And then you'll have broadband or spread spectrum noise come out, which is somebody transmitting a code, but it's spread across many megahertz, and it just bumps the system temperature up
Yeah.
a bit. And to know what's going on there, you just have to look and see what's going on. That's where you need to be able to have quite good resolution on what the levels in the passband are doing.
So with this SDR sharp, can I increase this resolution or these windows?
I don't use SDR sharp. I'm afraid, so I can't advise you on that. There are other people on the
Okay.
channel who probably
What
can do that.
else can I
Um,
use?
well, I'd start on. So this is 1420. You need to find a very bright source to get some confidence in your system, I think. So, and going back to your hot cold test. So what you have is you have the sky temperature at 1420, which is extremely cold the signal coming in. Then you have your and that's added to your system noise. And we'll leave it at that. When you have your when you go to a load, your system noise gets the load noise, the power coming out of the thermal, the voltage fluctuations from the load is added to your system noise. So that's that little increment that you should see. That's the change. And these changes are, I've always find as a professional, these changes and calibrations are fraught with uncertainty. You know, it's 3 dB plus or minus what. That's it. So you've got to develop some confidence in the way you do things. So do you have a signal generator?
No.
Okay. Is there anybody in the group that might have a signal generator to do things? I mean, you can buy small synthesizers these days and pop a signal into there, but I do a sanity check. So before we go onto the sky, which is always very tempting to race out and do,
Yeah.
I'd put a sanity check right through your receiver, so it turns up from a known generator, turns up at a reasonable power level. You can see the fluctuations go, and then you can get a feel for it, because the noise will raise your entire band, and it just you just want to know your on frequency, that the level you're putting in is reasonable, and you can see it clearly, and that gives you some confidence that you have an end-to-end system.
Can I make a quick recommendation here?
Yep.
And do you have stellarium?
Yeah. Yes.
Okay. And what is your are you pointing this south at 180 degrees?
No, there's no antenna connected at the moment. I'm just doing what Alex recommended.
Oh, well, that's your part. Okay.
So
Then
tomorrow I should try with the antenna connected.
put the antenna on. Look for, using stellarium, look for when the galaxy crossing passes. And then take this same picture.
Yep.
And see where the frequency or the beam is. Because this to tell you honest truth, this does not look bad for no noise. I mean, I don't see a lot of noise here. So I don't not quite sure what you're calling RFI here. You got that one blip in the middle might be your might be from that's a natural thing that comes from the
this is from the SDR, isn't it?
Yeah, it's from the SDR.
Yes.
Right. So you always get that center. That's why you're sort of off center, because that you always get that one blip there from the SDR. So
I would Ted over here. Mark, you've shared data with me, and I saw a galactic snake on there. So you're seeing hydrogen without a problem. It's just that at some times of the day, it was overwhelmed by other noise.
Yeah.
And just have to get more data to try to figure out if that's overcomable or whether you have to move. So
I'm going to try
I'd like to chat with you more about that and share more data back and forth.
Okay. I don't want to hog this meeting. Thank you for your advice, guys. I shall.
May I say one more thing? Have you got a directional antenna separate to your antenna that looks at the sky? Because you can pan around and directionally isolate where it is, and if you can move your gear to another position, if you get 3 positions, then you can triangulate and get a cocked hat, at least to know where your interferers are.
Yeah. Okay.
You get a triangle of the interception of the bearings, which might put it within a kilometer, depending how big a scale you're able to do.
Yeah.
And the accuracy.
Okay. So, thanks, guys. Sorry to take so much time.
No, that's what meetings are about. Do a certain amount by email, but I think it's good to raise issues face to face, and people can chip in along the way. So that's all fine. Anybody else got anything to comment on progress so far? I can guarantee, Mark, it's very.
Oh, it looks like we're losing
the right place. A lot of expertise within. So
okay. Yeah. Thanks, Paul.
Am I dropping out?
A little bit, Paul.
Am I dropping out?
Yes.
Yeah. Well, I'll do my bit quickly.
I'll stop sharing.
I'll do my bit. So I turn my video camera off. It might help. Rob, as I say, is an apology. Roger Heap was the other one I was trying to get hold of. He's got something on. So a couple of apologies there. I'm just going to quickly run through the muon detection project that I've been involved with. And I think I should be able to share my screen. No, I don't. It's not what I want. As I say, I'm not. Yeah, photos. No, cancel. I've got some photos on my email, so I need to share now. Let me broadcast the screen.
We see screen broadcast with a.
Yeah.
I
Are
see.
you getting the desktop now? See yourself?
There we go.
Now
We
you
see a
should be
beach.
Okay, and now you should be seeing Detector web page.
Yes, indeed.
Right. So this group, Detect, is based in Swinburne University in Melbourne, and they've developed a system of muon detectors, which they are being used in industrial locations. So they're being used for looking for cavities in solid material, whether it's down a mine looking upwards or in a building looking for cavities. They've even talked about looking for hidden spaces in the pyramids, those sorts of things. So the concept is that they're detecting muons, and muons are selectively absorbed so that they can actually, from below, they can actually change the angle of the detector and build a 3D image of what's above them in that particular location. So they've set up an education group called EduMod, and this is what I've been involved with. You can see their systems here. The two flat plates are two scintillators with a photomultiplier detector, one stacked above the other, so that because these scintillators will detect other particles, the theory is that a muon will go through the first plate and through the second plate. So if you get a simultaneous blip from both scintillators, that counts as a muon. And then the red box is the correlator, which collects the A and B signal and sends it out to USB onto your computer. You can also connect an oscilloscope, which you can see there, and each blip will appear on the oscilloscope. So then if I go to, just confirm that I'm getting through all right, I'm not dropping out.
We saw all that. You're back to the beach.
Yeah, back to the beach. That's Fiji, our favorite place. And so on the computer, then you run their software, their interface, which then produces a CSV file, which you can interrogate using Excel. Each blip, each muon detected by simultaneous scintillators is one line in an Excel spreadsheet, and it's got a whole lot of information. And the most important thing, it's got a timestamp. And so I ran it for 24 hours and got this graph. So you can see 0 to 24, not a lot of variation. If you look at the lowest 12,200 and 12,500, there is sort of a peak in the middle with that highest there, but you can see within 24 hours, you're getting 12,000 identifications. Then as part of their 5-day challenge, I actually ran it for 4 days and got this graph. So when you get one line per muon, you then order them by time, and then you do a count each time 1, time 2, time 3, and average the number of days that you've been collecting. So this is the average count across 24 hours, but collected data over so over 72 hours, and then average divided by 3. And you can still see that 12,000 average per day. But what we're getting now very clearly is that peak around about midday. So midnight, it's down at 12,100. At midday, roughly, it's up at the 12,350 nearly. And then it falls away again towards the midnight time. Basically, a curve there with a peak, trying to get hydrogen lines and so on. The more you run and the more you stack, then the clearer the image you're going to get. So if I get a chance, I'll run it for longer, and then we can do some more averaging. Let me just stop the share because Ted's looking at himself. So that share should have stopped by now. Go back to the gallery view. And so the one issue we've got is 3,000 Australian dollars, because they've been developed for commercial organizations. So I'm trying to encourage them, see if they can't do like a cut down version. The scintillator in their systems is 150 mil by 150. So a square scintillator, could they do 1/4 the size, for example? A bit like the ZWO electronics going into the C-Star 50. It's the same electronics you buy for the full-blown systems, but they've scaled it down and made a very affordable system with the C-Star robotic telescope. And I'm seeing if they can't do the same for schools and for amateurs with their Muon detector. They're a bit reluctant at the moment, but we'll see how far we can get with that. The other alternative I've suggested is that organizations such as the astronomical societies buy one each and put them so that they're streaming out to the internet, and then students can come along and grab that data. Or an organization like Victoria Physics, Vic Physics, can buy one and then lend it out to schools on a rotation, so spread.
Can I go back to your
where I'm at the moment with the Muon? Yeah, I can do that. I'll just need to share the.
Thanks.
Share the screen. Share the screen again. Fire up. Having a think. And if I go to my email. So is that coming through? Is that shared?
Not yet.
Not yet.
Paul, turn your camera off.
Right,
That helped last time.
You are sharing screen.
Now we see you are sharing screen.
That.
Yeah, turn your camera off, Paul. That helped last time.
Yeah, so you are sharing. Yeah, I've lost the stop video. Here we go. I mean, we've got 400 meg. I'm not quite sure why it's playing up. But if I go back to here, so there's the graph. Are you getting the graph now?
Yes.
Okay, far away.
So immediately I saw this, it reminded me of a total power interferometer drift scan. To me, it seems to be that there's two envelopes, at least two envelopes there.
Yep.
Is there any documentation around about the response of this machine? And there must have been people doing this for years on different other types of machines. And I'm just wondering why we have a sort of semi-repetitive peaking going on. I know nothing about this. I haven't done nuclear physics for a long time.
Yep, that's spot on, Duncan. And I've had the same question. That peak trough is absolutely periodic. And it's about what is it? It's how many hours is it? It's probably, is it 3 hours or something like that? It's something's happening.
So from my scientific experience, I'd be asking a question at this level whether it is machine based or instrument based, and how do we discriminate against that? Whether this thing needs to be buried in whatever absorbs the particles, buried in something for a sort of calibration. So this is very much like our I'm talking about as hot cold load tests, or putting the 50 ohms on the end of the sensor, getting a sanity check on what's going on.
Yep.
And I got a question too. This is 0 to 24 hours, so half this time you're looking through the Earth. So burying it, I don't think is going to do any good unless you got lead or something. But you're right; it does look like an interferometer. It's like, is this multiple detectors sort of lined up somehow, or is it just one pair detector? You know, how many detectors you got working?
It's one pair.
Oh, just one pair.
It's one pair, Rich. One above the other. And you can actually separate them and put materials in there. But the idea of having two of them is that if you've got a gamma ray, for example, it's going to be absorbed by the first detector and not get through to the second. So they're looking for simultaneity. They're looking for a pulse in both A and B at the same time. And that's what they count.
What about backscatter?
In terms of look through the Earth, what we're looking straight up are being generated by cosmic rays, which is isotropic. So it's coming in from all. It doesn't matter which way we're pointing. The only thing I would argue is that because there is a peak around 12, is there something coming from the sun that's adding to whatever is creating the muon flux? And that's the question that I've given them to come back with. I need to go back to talk to so much the engineer, well, the engineers to find out how they're doing the correlation, but also the scientists to work what the underlying theory is behind this. What, you know, is that a peak associated with the sun? And it's ironic that there is a reflection on my picture there, which looks like a sun anyway. And where's the periodic every 2 or 3 hours? Where is that up and down pattern coming from? For people in Australia, you would know the name Alan Duffy. Alan Duffy is the astronomer they bring out on television when there's something happening. Alan Duffy is the brains behind the system. And ideally, I'll get hold of Alan Duffy at some point and see if we can't make sense of this particular but yes, it does look like an interferometer pattern. And you're spot on, Duncan.
You got
Any
two
other
plates
around 2 plates, one above the other.
Yes. So what's the backscatter? You know, it goes through one plate and maybe absorbed, or multiples go through and you get some scattering back into the second plate. I just don't know how these things work enough, but you know, you've got to think about that. Yep. At certain angles, it might be more sensitive. 3 minutes and 56 seconds, I think, is going to be one of the things to watch for on those peaks. Difference between diurnal and celestial time.
Yes. Yep. Yeah. So that I've so far we've just been doing a trial of the challenge that they're going to set for school students. So at a school level, the the topic of muons is associated with relativity, because these muons have a finite lifetime. They can be created in the laboratory and they last for whatever it is, a microsecond or whatever. And because they're generated in the upper atmosphere, they shouldn't be able to get down to the Earth's surface. They should have decayed by then, but they do get down. So to some extent, it's exponential decay. There'll always be some left. But also it's relativistic time dilation. So because they're traveling at 0.99 something the speed of light, their clock, their onboard clock, their personal muon clock, goes more slowly relative to our clock on Earth. So they last for longer. And that's why the flux comes down to the Earth's surface. That's, as far as the school student is concerned, that's the bit that they need to know. From the muon's perspective, they, of course, are stationary in their own frame of reference, and the Earth is moving towards them. And because the Earth is then moving at 0.99 the speed of light, the distance between the muon and the Earth is shortened. So length contraction, according to the gamma. Gamma is quite high on these particles. So that's the physics that the school students need to know, but it's clearly raising questions beyond that. In particular, why is there a peak around midday? And also associated with that, why is there this repetitive up, down, very like an interferometer pattern? So I will continue to pursue this on behalf of myself and also on behalf of Sarah, so that I can ideally report back next time to see if I've got any progress. Any questions? Any other questions?
Yeah,
Yep.
sorry to dominate it, but it looks like it probably
right.
is a plastic sensor, a plastic scintillator.
I believe so.
Rather than a, say, sodium iodide crystal.
Yeah.
I
believe it's a sheet of white plastic.
All right, well, you sent me off down a rabbit hole for the rest of the week. I'll have a think about it.
Well, yeah, have a look at the that website.
Yeah,
I might be able to put the URL.
Um,
Just Google mdetect, mdetect, all one word, and you'll get to their website. Any other questions? Any other comments about the muon detection?
I've put 3 links in the chat, mostly related from work that Andy Thornett has done in the UK. They have the UK Radio Astronomy Group has provided a new kit, and it looks like 300 pounds with, I think it's got 2 scintillators inside. They are smaller, as you suggest. I encourage you to check it out. Lots of information on those 3 web pages.
Yeah. Yep.
Andy's talked about it with earlier Drake's Lounges.
And that's an alternative. I think for a while they were not able to supply them. I don't know whether they've now got new supplies and are building them again. I'm not sure. There was an MI. Sorry.
It was actually really interesting because I've just been with a bunch of engineers for 2 days about heritage engineering. And this is looking for voids in heritage engineering is actually ties into this. So interesting confluence.
Yes. Yeah, it's exactly what they're doing with their system, looking for voids in bedrock or in buildings or whatever. Yep. There was an MIT version. I think that's now defunct. I'm not quite sure, but the UKRAA was certainly producing muon detectors for much, much less than the 3,000 Australian dollars. So it'd be interesting to see if we can make contact with them.
From the look of it, the kit's been hardened.
They can give us an update on exactly what.
Okay, Paul, we lost you again. I'd say keep your video off.
Just the two of us.
Bandwidth.
Yeah, it's weird. We've got video, excellent internet here, but for some reason it's playing up. So that's the two from Australia, Rich. We've got, I think the Astronomical Society radio section, they're all busy doing stuff on the measurement from the dish very soon. So we'll get that on next month. So over to you, Rich.
Okay. Thanks, Paul. Hey, Johnny, what do you got going on? Mute.
Sorry. Yeah, I'm trying to find my mute. Not a whole lot other than what I'm just sitting here. I collected some very weak solar, and I'm just getting ready to send that out. But I don't have anything to add. I'm intrigued by the muon detector. That's an intriguing idea. Maybe it'll get to where us amateurs can get one just to detect some nuances, and I think that would be very interesting. But
yeah.
keep us posted on that.
Okay, thanks, Johnny.
I don't know that I'll live long enough to see that come to fruition. I don't know.
Well, go look at those links. The UK for 300 pounds, I think you can get one. So,
how much is 300 pounds in US dollars? About, you know?
No.
Maybe 20% more. No, £1 should be about $120, I think.
So it's
maybe 360.
Pretty heady amount of money.
Yeah.
All right.
All right. Thank you. Enjoyed it.
Thanks, Johnny. Don Latham. I don't think we got Don. Ted, what do you got going on? On mute. Ted? Here we go.
Oh, did I get through? I didn't have anything new. Thank you.
Thanks, Don.
Okay, Rich.
I'm pushing buttons trying to share something. Maybe that didn't fly. Let's try this one again. That looks a little bit better. So we got this scope in a box antenna mounted on a place where an old antenna got beat up by strong winds up in Estes Park, Colorado, so northwest of Denver, Colorado. And we're slowly scanning the sky, taking some long drift scans and plotting them on the sky. We've started the process again. I'll give more reports when we get more data.
Okay, thanks. Let's see, Helen.
Oh. Okay, can you hear me?
Yep.
Oh, okay. No, our next project is to now that we've got the scope in a box getting there, is where to put it outside. We gotta make a little ramp to get from the house over to where it would go, since I don't walk, so we're trying to figure out a way to work all that out. And it'll get worked out, it always does, but it just takes longer than you usually plan. But we'll get there, and I'll send you pictures when we get it there.
Great.
And thank you.
And by the way, anybody who has observations, I'm looking for them for this next journal. So if you get it to me by August 12th, we can get it in the journal as an observation, just a 2-page quick how you got it and what it looks like. And now I've got
Helen, I want to help you with your new antenna. So let's keep in touch. Ted.
We sure will. Thank you very much.
I might be able to run something up for you, Rich, on the Muon detector.
Okay, great.
I'll see. I need to write it up anyway, so I can certainly give you the 2 graphs and some background.
Perfect.
I'll aim to. Yep.
Perfect.
Okay.
Now I've got it. I think we got everybody else, but I've got my own little project that I was in the phased array stuff that has been going on, which is not interferometry, but it's phasing. I found, and let me share this. I found a phaser on the on eBay, and it's this thing for $30, and it's for the right frequency we need, and so what this will do is it'll actually change the phasing of the output signal, and it also has a an LNA on it. So it'll give you some it says up to 10 dB gain. Plus it has an 8-bit controller, so it'll allow you to digitally change the phasing on your signal. Now, the way we see these now, the only thing we use phasing for now, basically in amateurs, is the Radio Jupiter 2 antennas, where you've got one looking at the direction of Jupiter and the one behind it, and then you put a phase coil or a phase in there so that it beamforms in the direction of Jupiter at a certain elevation. Here you can do it automatically with a computer, and you can add more antennas onto it and I ordered 2 of these. And so what my plan is to set this thing up with 3 antennas. One will be, and they're all going to be looking straight up. So basically I have a 30-degree from, at first from straight up. And then I have the computer phase these things so that I can automatically shift the beam from 0 or from whatever to 90 degrees elevation, actually 120 degrees elevation, and then hook all this stuff up into Ted's software system and see if I can get this thing to automatically beam steer where I want it to without having to move an antenna. So that's my goal. And then you can always add more antennas and more of these things and get, multiple beams going. I mean, multiple antennas beam forming all the time. And then you can continuously moving continuously moving. So that's sort of what I'm thinking here. We'll see if it works.
Rich, it will work.
Yay.
I would give you, I've done this with antenna before to get them to point properly, like calibrate on the sun. What you do is technique of nulling technique, whereas one antenna is pointing in its normal amplitude, straight ahead. You flick the phase and find the null for 180 degrees. So you null out the signal and then you subtract off 180 to get that. So you return to the maximum. The nulling technique is very sensitive for getting a good result. The thing that you do need to make sure is the magnitudes of the signals of the vector that's coming in are both the same in each antenna, which means you do need to somewhere along the track, scale the gain to get the same at levels. But we used to do this inside the primary beam of the phased array. So yeah, what you'll find is whatever your antenna beam width, you'll be able to electronically move the beam around inside that, and it's much easier to get good precision and accuracy of where you're pointing with this technique.
And I'm thinking about Ted produced an interferometry video where he had 3 antennas that he made with a little like Alex's little phased array, or not phased array, but circular antennas.
Disc Yagi.
Yagis,
Yagi.
yeah, the circular Yagis. So I'm thinking, Ted, that if I get 3 of those, aim them straight up, and hook these phasers on them, and then I should be able to beamform, take 10 minutes and then have it automatically move 5 degrees in the beam using the phasers, and I should be able to populate the galactic map really fast. So that's my plan.
I suppose that's true, of course. If you're doing it faster, then you have more noise, but okay. And I just have to say, I think you're so lazy, you don't want to go out and change your antennas, but okay.
That's my job, is to not do physical labor. That's why I'm retired. And, as a Sarah president, I don't have time to do physical labor. I'm doing bureaucracy. So this is my way to get around that.
So you have an excuse. All right.
I have an excuse. The rest of you guys have to go out in the cold and the heat and move antennas, but I'm planning on not moving antennas physically anymore.
That's not radio astronomy. You don't get up you go to sleep at night.
Yeah, that's right. That's right.
There are a few other keywords I might add to that. Is rotating lobe interferometry, which was early in the piece in the 1950s and 60s. So that might be words to search on.
Rotating lobe interferometry.
Lobe, L-O-B-E, yes.
Lobe, okay, sure, that's pointing. All right.
So you're actually rotating the fringe pattern by changing the phase. It was done at, I've actually done it, but but when you're using a phase switching interferometer. It's dark age stuff, so I can't remember the details.
So I guess the question is, why haven't people been using these phasers in amateur radio astronomy? It seems like this would be a natural approach, especially it seems so cheap.
My take on it is you have to go from, okay, well, if I was doing it and you alluded to having multiple beams, then there's things called a Butler matrix, which is a bunch of resistors, which is a bit oddball, but it's an analog system. So in the radio receiving system I'm experienced in, you came in from the telescope at an IF frequency, you digitized the signal. I got to remember this correctly. Converted it down, you brought it in at an IF frequency, converted to baseband, digitized it to a few bits. Then you put in a circular memory, or first in, first out memory, where you can actually program where you pick the data up, and that data then gets shot out the back to a high-speed digital to analog converter. Then we did phase rotation by chipping out the phase on crystal locked oscillators, and then we fed it into this massive Butler matrix of 15,000 resistors. And out of that, we put in 88 inputs. We got out 64 real-time beams on the 128 real-time beams on the sky. So so it gets really complex, and I think the point is all that is now being shrunk up into a chip. I mean, you might use the Butler matrix on the back, or you might use a digital Butler matrix to do beamforming or equivalent, but it's all been shrunk down, so you can now do it.
Good. It looks like I can hook at least 3 antennas to the same, or I mean, just like Ted did with his interferometer, three circular Yagis to these three phasers to LNAs to the SDR, and then have them fed into the TED software. And the only question would be is when I beamform, I would send out. I have 8 bits on each of those phasers to tell me what angle I want to change it to, and then how would I be able to tell TED software what elevation I'm actually looking at automatically, or do it? Ted, how do you right now? Do you just manually put in the elevation in the software?
You can enter it on the command line. You can change it on the graphical screen. But talk to me. We have ways.
Yeah, because it looks like when I send the signal out to change the elevation from the beam, and I send that out to the beamformers, then I know what the angle is I'm aiming at. I can have it sent to the software, and if you can accept it, then we've got an automatic system.
Yeah, we're working it up so that if you can log where you think you're pointing in some text file along with a timestamp, then we can always improve the data file with that information later. We kind of zip them together, second by second kind of concept.
Well, I would know that because that's the input. I'll have automatically.
Yeah. So you
Move
just make a
that.
log in a text file where you think you're pointing. Let's find out if it works. But yeah, and then it just gets zipped into a data file as a second step later on.
Perfect.
There are ways right now, I guess.
Okay. All right. Well, that's my plans and my lazy astronomer's approach to beamforming without having moving antennas. So, and you'll notice I'm also going to point them all straight up. So I'm not going to. It's going to be very easy. I don't have to have moving antennas. I just have multiple, and I can add as many antennas as I want, depending on the number of phasers I want. It could actually be very well. I'd have a farm of antennas looking straight up.
Just remember, when you get a farm of antennas, it never goes quite as well as you expect because there's always a number of gremlins gnawing at you.
I get it. I'm going to start with 3, maybe 2 first, and then work my way up.
If you can do multiplying interferometry, I don't know what you've got, because one of the things I think you're moving very close to is an SDR with multiple inputs. If you can do that, you can solve the phase triangle. You should get 180 degrees around the triangle between antennas. Anyway, it's
the way
probably
Ted
a talk for another time.
He took the analog input and just combined it, and then the output of that went to the SDR.
Yeah, so that's a sort of a total power interferometer.
Right.
Rather than you've got the DC component as well as the AC component. The fringe gets superimposed on the total power or whatever's going on in the beam.
Yeah, I had an adding interferometer. It's also just known as a phased array, so it was a fancy word for it. And combining is a very polite term. I shorted them together, so yeah, it did something.
Yep.
I got fringe patterns, and I learned a bunch.
See, but I don't think I'll have fringe patterns because I'm going to line them up north to south. And then my goal is to basically look along the meridian and be able to beamform along the meridian. And as everything passes, I can go up and down the meridian.
Have a look at the Chime site, Canadian Hydrogen. I can't remember what the thing is.
Yeah,
The
just
chime
build one of
site.
those.
It's getting very close to what they do. They basically have their cylindrical collectors aligned north-south, and they collect data from that. But I will caution you about confusion in what you're doing, and not confusion in your intellectual confusion, but confusion because of all the other background objects in the sky. People forget that radio astronomy's diffraction optics against photon optics. If a photon misses your mirror on your telescope, it's gone forever. But our antennas see all over the sky at some level.
Okay. Well, thanks, Duncan. Adrian, you just
Pleasure.
popped in. You got anything going on? Adrian? All right. Well, thanks, everybody. I think that's everybody. And we'll see you in 2 weeks on the RTOP. And don't forget, if you got an observation report, I need that by August 12th. All right. See you, everybody.
Thanks, everybody.
Thanks. Been great talking.